We usually think of the ground right beneath our feet as completely solid, permanent, unmoving. But the reality is, we are living on a highly restless planet. And when that ground inevitably shakes, you really have to wonder, why is it that two seismic events with nearly the exact same magnitude can cause such vastly different levels of devastation? Why does one city stand tall while another is just completely reduced to rubble? Well, welcome to this explainer, where we're going to break it all down. So let's dive right into this pretty startling mystery from 2026. In April of that year, a massive magnitude 7.4 earthquake hit the Sanriku coast of Japan. The death toll? Zero. Literally zero. But then, fast forward just 2 months later, a 7.5 magnitude earthquake strikes Yaracuy, Venezuela, and the death toll there was a tragic 1,450 lives. We're talking about two quakes almost identical in raw power, but with entirely opposite outcomes. All right, let's look at Section 1, the restless Earth, focusing on the seismic landscape of 2026. To really understand why this happened, we first need to zoom out and look at just how wildly active the planet was that year. And as you'll see, the sheer power of the Earth is really only half the story. The death toll almost never aligns perfectly with the Richter scale magnitude. Take a look at Afghanistan. A 5.8 quake tragically claimed 12 lives. Meanwhile, the Philippines endured a massive 7.8, but saw 82 deaths. And then there are our two focal points, Japan at 7.4 with 0 fatalities, and Venezuela at 7.5 with nearly 1,500. Now, it's absolutely crucial to remember that our planet's outer shell is this dynamic, moving system of shifting tectonic plates. It's like a giant, slow-moving jigsaw puzzle. Quakes generally happen at 3 types of boundaries: convergent, where the plates are colliding; divergent, where they're pulling apart; and transform, where they just slide right past each other. Because 2026 had so many quakes, you might be thinking, was this some kind of global chain reaction? Actually, no. Experts confirmed these were entirely independent events, just localized releases of built-up stress. Moving right along to Section 2, the science of shaking and those intense underground forces. Before we can really compare what happened in our 2 case studies, we have to establish the basic science of how these immense underground forces translate into actual destruction on the surface. In Japan, the Sanriku quake happened at what's called a subduction zone. This is a convergent boundary where the Pacific plate is actively shoving its way beneath another plate. Imagine stretching a massive underground rubber band as it dives down, until eventually, it snaps. That snap released a sudden 12-second burst of incredibly intense seismic energy. Venezuela, on the other hand, faced a uniquely terrifying, completely different phenomenon. It's called a seismic doublet. This is an ultra-rare, incredibly devastating scenario where 2 massive tremors hit the exact same region in rapid succession. So a 7.2 magnitude quake hit, and then, just 39 seconds later, boom, a 7.5 hits. Before the buildings could even begin to stabilize from that first violent shaking, they were battered all over again. It's a 1-2 punch that exponentially increases the risk of total structural collapse. Which brings us to Section 3, a tale of 2 quakes, where we put Japan and Venezuela head-to-head. When we place the specific data of these 2 events side by side, the plot really thickens. The variables beyond the magnitude tell the real story here. Japan's quake originated a fairly safe 35 kilometers deep, way offshore. But Venezuela's quakes, they were dangerously shallow. We're talking between 10 and 21 kilometers deep, meaning that explosive energy didn't have room to dissipate before it hit the surface. Plus, the Venezuelan epicenter was right next to Caracas, which sits on soft river soil. Think of that soil like a bowl of jello. It actually amplifies the seismic waves, whereas Japan's infrastructure largely sits on much firmer ground. Let's move to Section 4, Japan's blueprint for engineering survival. Okay, but geography alone doesn't save lives, right? 2,500. That is a staggering number. That's actually the number of earthquakes Japan experiences every single year. Because of that extreme frequency, Japanese society is literally forced to treat seismic activity as an everyday reality, not some rare anomaly. They simply cannot afford to be unprepared. Driven by super strict laws and a culture that has absolutely zero tolerance for construction corruption, Japanese buildings rely on a trio of highly advanced architectural systems. You've got Taishin for your basic structural resistance. Then there's Seishin, which uses these massive dampers to actively absorb vibration. And finally, Menshin, which is this incredibly cool base isolation technique that physically decouples the building from the movement of the ground. Essentially, they build their structures to sway flexibly like a tree in the wind rather than snap like a dry twig. But hey, survival is about way more than just architecture. Japan's automated early warning system is an absolute marvel. The second the meteorological agency detects those initial faint tremors, alerts blast out to every citizen's phone in a matter of seconds. And it's all automated. The Shinkansen bullet trains instantly slam on the brakes to avoid derailment, buying people precious life-saving seconds to take cover before the destructive surface waves even arrive.
Now, contrasting that entirely, we have Section 5, the Venezuelan tragedy, a truly cascading catastrophe.
Unfortunately, a lack of resources can turn a purely natural event into a devastating human catastrophe. Sources indicate that years of severe economic instability and international sanctions left Venezuela without the necessary funds to maintain their infrastructure. Over in Caracas, you have highly vulnerable, unregulated, informal housing built on peripheral slopes sitting right alongside older concrete buildings from the 60s and 90s. Without the money for ongoing maintenance or modern seismic retrofitting, these structures were practically sitting ducks. Furthermore, reports highlight the corruption within the construction sector heavily compounded this vulnerability. We're talking about the use of cheap, substandard materials and the outright ignoring of vital building safety regulations. That meant many of these buildings were fundamentally incapable of resisting any kind of shock. So when that dangerously shallow double quake hit the soft soil of Caracas, those compromised structures just folded like houses of cards. Which brings us to our final segment, Section 6, Building Resiliency and the Defining Lesson We All Need to Take Away. As global rescue operations rushed in to clear the rubble in Venezuela, we did witness some really incredible acts of human solidarity. For instance, India launched Operation Amistad, which translates to friendship, dispatching military aircraft packed with urgent medical aid and equipment. But we really have to recognize that while international aid is absolutely critical for immediate relief, it is ultimately a reactive measure to a completely preventable problem. And that perfectly illustrates the core takeaway of this explainer. As the quote says, earthquakes cannot be prevented, but their impact can be reduced through strict building codes, earthquake-resistant infrastructure, early warning systems, and public preparedness. The earth is going to shake. Tectonic plates are going to keep moving. But the choice of whether our cities stand tall or fall flat, that's entirely up to the engineering we use and the laws we strictly enforce. So I want to leave you with a bit of a provocative thought to chew on. If the shifting of tectonic plates is completely inevitable, but the collapse of the buildings we live and work in is preventable, are these really natural disasters at all? When we have the technology and the know-how to survive, who is truly to blame when a city falls? Think about that the next time you feel the ground move. Thanks so much for joining me on this explainer, guys. Keep questioning, keep learning, and we'll see you in the next one.